Today we are going to be reviewing for test number 3. Now test number 3 will be over sections 1.5 through 1.8. Now the first topic that we're going to be looking at today is domains. How to identify the domain? Where will the domain be restricted? Now there are two situations that cause the domain to be restricted. The first one is when I have 0 in the denominator. I cannot have 0 in the denominator. So oftentimes we have to take whatever the denominator is, especially if it's a polynomial, and set it equal to 0 and solve, and then we have to restrict the domain from there. The second situation is when I have an even indexed radical. An even index would be like 2, 4, 6, any of the even indexed radicals. Now in that type of situation, I need to take my radicand here, set it greater than or equal to a 0, and solve it. Okay, so let's go ahead and take a look at a few examples here. And we're going to be taking a look at this one here. Now, in this problem here, I see I have f of x equals 2x plus a 3. Now, look at the denominator. I do not have a polynomial in the denominator. So, the first situation, as I said here, does not exist. Also, look here. Do I have a radical? Well, no, I don't. So, that tells me that my domain is going to be the set of all reals. Now, for our second problem here, we're going to take a look at this one, and I see x plus a 4. So I'm going to take that x plus a 4 and set it equal to 0 and solve it. Okay, so if I take that equal to 0 and solve it, I will get x is not equal to a negative 4. Okay, so the way I would write that in interval notation, negative infinity to negative 4, and then negative 4 to infinity. Now here's a problem where I have a radical. Okay, now notice you don't see an index there. That means it's square root. So for this radical, you're going to take that radical and radicand, I should say. So you have the 4 minus x squared, and you're going to take that 4 minus x squared and set it greater than or equal to 0. Then you're going to solve it. And when you solve it, notice first of all I multiplied both sides by negative 1, and then to get that x squared to be positive, as shown right here. Then I need to solve it, and when I solve it, I am going to find the critical values. So the critical values are plus or minus 2. Now remember, anytime we solve for a quadratic inequality, we need to set up a chart and determine, okay, what interval do my solutions exist in? So now I've set up a chart here already here for you, and you can see it as you look at it here. And looking at the chart, I will have this region here, which is negative infinity to negative 2. This region over here, which is 2 to infinity. And in here, negative 2 to 2. Now, if you use the text method, which is right here, you could set up a chart. Okay, so that's what this piece here is. That's the chart method that your textbook talks about. If you take a value from each of these intervals and substitute it in, and I would substitute it in right up here, you can determine that it's going to be true in this interval right in here. So that tells me that the domain of this function will be any values between negative 2 and 2 inclusive. For this topic, we're going to graph a function, and then we're going to find its domain and range. Then we're going to evaluate the function at a given value. So first of all, looking here, we've been talking about the domain of a function. Now, if I were to graph this function first, instead of just using the properties that we just talked about here, if I were to graph this function, my graph would look something similar to this. Now, I can take a look at this function and just observe to see where the domain exists and where the range exists. My domain here is going to be as I see right here. Notice I can take my denominator, I can take my radicand, I can set it greater than or equal to a 0 right here, solve for it. So I see my domain is going to be x greater than or equal to a 1, as you can see from the graph. Now, from here I can also, so my domain is going to be 1 to infinity, including 1. Now, for the next area, it would be the range. So what we're going to do for the range is I'm going to just observe the graph. Now again, pretend like you're a little person walking along the y-axis here, and you're going to look right or left, and where do you see the graph? So as you walk up here, you start to see the graph at 0, and then you see it from 0 to infinity. So that tells us that our range is going to be from 1 to infinity, starting at 1. Now, the next thing it would ask is evaluate it at x equals 1. When we evaluate it at x equals 1, I'm going to plug 1 into the function. In plugging 1 into the function, then we're just going to simplify it, and of course the square root of 0 is simply just going to be 0. In this example, here's another type of function, and we have in this case 4 minus x squared. Now, because we have a 4 minus x squared, hopefully you identify that it's going to be a quadratic function, which means it's a parabola. Okay, so here's what it looks like. In knowing this, we can look, and hopefully you remember from that parabolas, the domain is the real number system. Okay, so there's no restriction on the domain. Okay, so you're going to indicate by saying negative infinity to infinity. However, the range, again, your little person walking along the y-axis, and you start to see the graph right there at negative or at positive 4, and then you see that graph all the way down to negative infinity. So that tells us that our range is going to be from negative infinity to a positive 4. Now, this problem asks us to evaluate it at x equals 0, which means I'm going to plug a 0 into the function and simplify, and I will get f of 0 equals a 4. Our second topic today is we're going to look at equations to see whether the equations are functions or non-functions. Now, I have a vertical line test. A vertical line test is one of the ways to determine whether an equation is a function or a non-function. Now, what a vertical line test does is it tests a set of points in a coordinate plane to see if y is a function of x. Now, y is a function of x if and only if no vertical line intercepts the graph at more than one point. Now, my first equation is y equals x squared plus a 2x. This is a parabola. Now, it's a parabola and it says y equals. That means it's a parabola that opens up or down. And because it's a graph that opens up or down, yes, it is a function. Matter of fact, it is a square function. So, in this situation here, it does pass the vertical line test. That is why it is a function. Now, oftentimes if you don't recognize right away whether an equation is a function or not, we can graph it. For example, in our second problem here, I have y equals x cubed minus 1. Is it a function? So, I graph it, and we're going to determine what it's going to be. And we can see, yes, it is a function, because if I use my vertical line test here, and let's go ahead and see if we can do a line here to show the vertical line test. Okay, so if I put a line straight up and down here, and I'm going to take that line and I'm going to move that line across. And notice if I only touch the equation just once, then yes, it is a function. So my reasoning here is yes, it is a function. And why is it a function? For this reason right here. It passes the vertical line test. Now what about this one right here? I see x minus y squared equals 0. Is that a function? Well, the first thing I want to do is I want to solve it for y. And when I solve it for y, it'll look something similar to this. So I have y is equal to plus or minus the square root of x. So I have this one here and this one here. There's the plus or minus. Now if you enter that into your graphing calculator, and by the way, because you have a positive radical x and a negative radical x, you have to enter it into your graphing calculator at one as y1 and the second one as y2. Now when you do so, you're going to find that it is not a function. Why? Because if you put a line right down the center, notice you're going to see at any point, for example, at this domain value right here, we have two range values, one here and one down there, which means it does not pass the vertical line test. For this topic, we're going to be looking at odd and even functions. Now, for an odd function, remember, you're going to show symmetry to the origin. In other words, you're going to plug negative x in for x, negative y in for y, and see if it changes it. For an even function, you're going to show y-axis symmetry. In other words, you're going to plug negative x in for x and see if it changes it. Alright, so let's go ahead and do a problem here and see if it is an even or an odd function. First of all, for the first one, let's do the even function test first. So I am going to plug a negative x in for x, and then I'm going to simplify it, and then I'm going to compare the original to what I have here. Did it change it? And yes, it did. So I write my argument, and my argument is going to be something like this. Therefore, it's changed, and it is not symmetric to the y-axis. Thus, it is not even. Now, make sure you can write this type of argument, please, on your exam. Make sure you can show that argument. Okay, now, what about the odd function? Well, to determine if it's an odd function, again, we're going to plug negative y and negative x in, and then we're going to simplify it, and we compare. Now, notice here, and compare that with what we had. It did not change it. That tells us that it is odd. Why? Because it is unchanged, it's symmetric to the origin, thus that means it is an odd function. Okay, for this example, I have f of x equals x cubed minus x plus 1. Let's see if this is odd, even, or if it's neither. So again, first thing I do is I plug in a negative x for x, then I'm going to simplify it, and now we're going to compare this here with what I have down there. And what did I see? Did it change it? Yes, it did. So make sure you write your argument. Your argument needs to be very similar to this. Don't just say it's even. Make sure you say why it's even. For example, therefore it's changed and it's symmetric to the y-axis. Thus, it's going to be not even. Okay, so now let's do the test for odd. So again, you plug negative x in for x, negative y in for y. You're going to simplify it. After you simplify it, now you're going to compare what we have here with what we have here, and it looks like it's different right there. I have a plus 1 and a minus 1 down there, so it did change. So I'm going to say, therefore, it changed, and it's not symmetric to the x. Thus, it is not odd. So this means this situation is neither. In this slide here, you see the different common functions that we have available. Make sure, as you're graphing each of these, to be able to recognize what is a constant function, what is an identity function, what is an absolute value function. Every absolute value function looks something similar to what I have right there. Every square root function looks something similar to what I have here. Every square function looks like a parabola, and every cubing function looks something like this right here. Alright, so know the different types of common functions. In this slide, we're going to take those common functions and we're going to do some rigid and some non-rigid transformations on these functions. Now, let's just review this slide here for a second. If I take the function and I add a c value to it, it shifts it up. If I subtract a c value to it, it shifts it down. Now, if I take the x and I subtract c, notice, in this situation, it's before the prevailing operation. So it's going to give us something we do not expect. So if I see x minus a c, that means instead of it shifting to the left, as we think might happen, it's going to shift to the right. Likewise, if you see x plus a c, then it's going to shift to the left, a c value. Now, the reflections. If you turn the whole function negative, that whole function negative, that's going to reflect it over the x-axis. However, if I plug a negative x in for x, or in this situation my x is turned to a negative x, that means it's going to reflect it over the y-axis. Now, what about the non-rigid transformations? Well, the non-rigid transformation, if I times my function by any c value, what that's going to do is that's going to change it. So it's going to either vertically stretch it or vertically shrink it. Now, it stretches it vertically the larger my c value becomes, above 1. And when my c value is between 0 and 1, it vertically shrinks it. Now, I did put a little example here that notice vertically stretch is the same as horizontally shrink. and vertical shrink is the same as horizontally stretch. So whichever way you want to say that. So let's take a look at our first example. I have y equals the cube root of negative x. Now, what did we say here? I see a negative x. So what does that tell you automatically? Well, that means it's going to reflect it over the y-axis. So let's remove this, and you're going to see it's a cube root function. Normally that cube root function would look something like this, but because of the negative x, it reflects it over the y-axis. So what has happened to it? Well, it reflected it over the y-axis. Okay, in the second function, again this time, what do I see? Well, it's a cube root again, but this time it's absolute value of x minus a 1. So, notice that minus 1 is underneath the radical. That means it's before the prevailing operation. So what that means is it's going to shift it right, left, or up and down. Well, hopefully you said, oh, it's going to shift it right and left. Now, how is it going to shift it right and left? Well, remember, it's what you do not suppose. So that means you see a minus 1, so it's going to shift it to a positive 1. All right, so here's how you're going to say it. It shifts it right 1 unit. Okay, so now here you have a negative 3 before the prevailing operation, but then you have the 1 here, okay, which is after the prevailing operation. Well, here the x minus 3, right there you see it's going to shift it. You see it's a minus 3, so it's going to be what you don't suppose, which means it's going to shift it to the right 3. Then you see up 1, and that's after the prevailing operation, so it's going to shift it up 1. So that graph is going to look something like this. So notice it shifted over 3, up 1. Notice it's just a plain square root, not a cube root, which means it just looks like what I'm tracing right now. So how are you going to describe the transformation? Well, it shifts it right 3 and up 1. All right, let's take a look at these 3 examples. In the first one here, I see a square function. So I know it's going to look as a parabola. I see a negative there, which means, and notice my negative is before the x. So it's going to be negative 1, and then it's going to be x squared minus 3. Now, is there anything before the prevailing operation? No, there isn't. I see a plus 3, so that means it's going to be, that's after the prevailing operation, which means it's going to shift it up. Now, because it is a negative 1 in front of that x squared, and guys, it is a negative 1 in front. Okay, in other words, it looks like this. Negative 1, and then parentheses, and then it's going to show the x squared plus a 3. Now, notice very carefully that negative 1 means instead of it opening up, it's just going to open down. So that tells me that my function is going to look like this. And what had happened? Well, it shifted up 3 and it opens down. Okay, let's take a look at our next one. The next one here is another square function, but notice it is a 2 in front of there, which means you're going to vertically stretch it some. So, because it's going to vertically stretch it, that means it's going to become thinner. So the graph is going to look like this, and it's going to be a little bit thinner. Okay, so notice I said vertically stretch, but you know that's the same as horizontally shrink. All right, and in the next example, again, it's a parabola, but this time it's 1/2 in front of there, which tells us that is going to horizontally stretch, or you could say vertically shrinks. Okay, so here's what the graph is going to look like. Notice it's much wider. Okay, and of course it's going to horizontally stretch. For this topic, we're going to look at some arithmetic combinations of functions. In other words, we are going to add functions, subtract them, multiply them, divide them, and then we're going to do a composition of functions. Okay, so we're going to perform these 5 operations on functions. On this slide, we're going to add and then subtract. But then notice I'm going to plug in a value for after I add it and subtract. So I'm going to plug a value of 2 into the new function. Okay, so looking here, I have an f function, I have a g function. Now I want to add these two functions together. So when we add them together, I will simply get, now notice when I'm adding together, I am just adding, I have x squared, and then I have 2x plus 2x gives you 4x, and then I have plus 1 minus 1 gives you 0, so I have x squared plus a 4x. Now I want to know what will it be if I take that resulting function and I plug in a 2 in there. Well, we're just going to substitute a 2, and then I just use order of operation, and I get 12. Alright, now, next we're going to subtract them. When I subtract them, I take my first function here, subtract my second function from it. Now I'm going to distribute in my negative, and in doing so, I'm going to then add like terms, and I end up getting negative x squared plus a 2. Now, let's evaluate that resulting function with a value 2. So that means I'm going to plug a 2 into my resulting function, and then use order of operations to simplify it, and I end up getting a negative 2. In this slide, we're going to multiply and divide. Okay, so again, we have the same two functions. I'm going to multiply them together. So that means I'm just going to put the binomial in the front and the trinomial, and now I'm just going to distribute and add like terms. Okay, so it's going to look like this when I distribute in, and then when I add like terms, it's going to look like that. Alright, and that is multiplication of these two functions. Now let's go to division. For division, we're going to put the 2x plus 1 on the top and the x squared plus the 2x minus 1 on the bottom. Now, there's a special note here. Normally, we would have to use long division to simplify this. But notice here, my degree of this polynomial on the top is smaller than the degree of the polynomial on the bottom. Because that exists, I put a special note here, you do not need to simplify it further. For this slide, we're going to find the composition of functions. Again, the same two functions. Now, because it says f of g of x, that means I'm going to take this g function and I'm going to plug it in right here where the f is in this function. Okay, so here's what it's going to look like. Now, after this, then I'm going to distribute my 2 inside, and then I'm going to combine like terms and simplify. Okay, so it looks like that, and then here I can add the negative 2 plus 1 together, and that's what I get. Now, we're going to evaluate it for a value of 3, which means, now, the way you do this one again is we take our resulting function right here, and I'm just going to plug a 3 in for the x's. And then I'm going to use order of operation and simplify it to get 29. For this slide, we're going to look at how to find inverse functions. Now, first of all, a function f has an inverse function if and only if no horizontal line intersects the graph of the function at more than one point. Now, what does this mean? Well, that means if I have a coordinate plane here, and let's say that I have a parabola right here. If I use the idea of a horizontal line test, and I'm going to put my horizontal line right through there, and as I move that horizontal line along the y-axis, if it touches the graph more than once, as it did in this situation, that means I do not have a one-to-one function, which means that function, does, as it sets, does not have an inverse. So we would need to restrict the domain first. And in this situation, notice if I restricted it from the domain value of 0 to infinity, then I could find the inverse of that function. But as it sits, I cannot. Alright, so let's go ahead and walk through the steps here of what we need to do to find the inverse of a function. First of all, you want to write y for f of x. Then you want to interchange your x and your y's. Thirdly, you want to solve the equation for y, if possible. And lastly, you want to replace the y with your f inverse. Now, don't stop there. Yes, you have found the inverse of the function, but we need to prove that they are inverses. So you're going to use the composition of functions to prove it. So you're going to plug in your inverse function into your function, and then you're going to plug your function into your f inverse function, and you're going to verify that both of them equal x. And if that's the case, then they truly are inverse functions. Now, a little hint. You will have a question on the test that deals with this. Yes, you're going to have to find the inverse of a function. And then you're going to have to perform the test of the function. And thirdly, you're going to have to be able to graph both of them and show that it was a reflection over y equals x. Okay, so find the inverse, then you're going to graph both, and then you're going to prove they are mathematically. Make sure you can do that. I promise you that question is on the exam. Okay, let's take a look at this example. In this example, it says determine whether the function has an inverse function. In other words, is it one-to-one? And if it is not, we need to restrict it. If it does have an inverse, we're going to find its inverse function. And then we're going to verify it through a proof. Okay, so first of all, looking at this function, hopefully you can see and you can recognize that this is kind of like a parabola, but it has a little bit of a flat bottom on it. So that means it is not a one-to-one function. Why? Because if I put a horizontal line test through here, I would see that every range value right here has two domain values, which means it is not one-to-one. So we need to restrict the domain. So my domain I'm going to restrict, so it's going to be from 0 to infinity. Okay, so there's the domain we're going to restrict it on. So now, after restricting the domain, now I can go ahead and I can interchange the x and y's. I can solve for y by taking the fourth root of both sides, and then I can replace the y with the f inverse. Now, after doing that, now it's our turn to prove that. So I'm going to use the rule, and I'm going to plug f inverse in for f, and I'm going to simplify it. Okay, so notice here I have the fourth root of x in. I plugged it in for x to the fourth, and the fourth root to the fourth power equals x. Okay, so according to looking at it this way, it does equal x. Alright, now I'm going to do the same, but this time I'm going to plug the function into the f inverse function. In doing so, notice it looks like this. I plug my function into the f inverse function, and it gives me x. Therefore, my argument is, since f of f inverse is equal to f inverse of f of x, and they both equal x, then they are inverse functions. Now, this argument is very important for you to know. So make sure you practice enough with this argument so that you can be able to quote that argument for me at the end of your proof. Okay, let's try this example. Now, first of all, think of this. What do I know about this? Is it a function? Is it one-to-one? Yes, it is a function. How do you know it's a function? I called it a function. Is it a one-to-one function? Well, yes it is. How do I know it's a one-to-one function? Well, we know it is because this function here is a radical function, okay? Which means it is related to this common function that looks something similar to that, and that is one-to-one. Therefore, this one will be one-to-one. Okay, so I do not need to restrict it. Alright, so next thing I'm going to do is I'm going to interchange the x and the y's. Alright, then we're going to solve it for y, and this is what it's going to look like once you solve for y. So notice what we did. I squared both sides, subtracted a 3, divided by a 2, and I'm left with this. Now, let's use our symmetric property, flip that around, and I'm going to replace y with f inverse. So there's our inverse function. Now, at this point, make sure you can graph it. Okay? Make sure you can graph it. Now, you know here, when we graph it, you know here that if I draw the line y equals x right up through there, and I'm kind of running a little bit out of room, you know that my inverse of my function is going to be a reflection over that, which means my inverse is going to look something similar to that. Okay, so that's a little bit of what the graph is going to look like. Okay, now on your test, make sure you can do the tests here. Make sure you can find the inverse of it. Then make sure you can graph it as I did right up there. And then next, make sure you can prove that they are inverses algebraically. Okay, so let's go ahead and do that. So first of all, I am going to plug the inverse function into the f function, and I'm going to simplify it. So I plug my inverse into the original function, then I'm going to simplify it, and notice I get x. Alright, so that's good. That's good. I was hoping that would happen. Next, we're going to plug the function into the f inverse function. In doing this one, notice here's my function, and I'm plugging it into the f inverse function. Then I'm going to use order of operations and simplify it, and I get x. Wonderful. Now we need to do our argument. And our argument will look like this. Therefore, since f of f inverse is equal to f inverse of f of the function equals x, then they are inverse functions. Please make sure you can do this, because this is a large part, a large section of the test. There's a lot of points right there. Please make sure you can do that. Okay, we are almost done here today. All that's left is the application problems. Now, the two example problems that I pulled here are some of my favorite from the text because they will require you to be able to use your graphing calculator. Okay, at least on the first one anyway. So let's take a look at the first one here. And it says a profit function p of x for a company selling x item is given by this profit function right there. It says determine the number of units that will maximize profit and also determine the maximum profit. So I want to determine the number of units that will maximize my profit. Okay, so first thing you want to do is you want to graph the function. Okay, so let's do that. We're going to graph the function. So I use my graphing calculator and I graph the function, and it looks something like this. Next, I'm going to play with the window. Now, you need to just, when you first graph it, it may not look like this. Matter of fact, it probably won't. So you're going to have to play with the window in order to get something so you can see the x-intercepts here and here. So you can see the maximum as I showed there. Now, the window that works with that is shown right here. You have to play with your window setting in order to get a graph that matches it nicely. Alright, next thing we want to do is I need to determine this maximum point. In order to find that maximum point, I'm going to find that maximum point. Now, after I told my calculator to find that maximum point, it gave me an x value of about 60 and a y value of 9,300. Alright, now what does that mean? Well, see that 60, that is this right here. Okay, it's going to give me 60 and then it's going to give me 9,300. That means my maximum, in order to maximize my profit, I need to create 60 units and sell 60 units to maximize my profit. Alright, so now how do I write that up? Well, here's how we're going to write it. If the company sells 60 items, they will make a profit of $9,300. Okay, we have one more application problem left. Now, in doing this one here, let's go ahead and read it, and then we're going to see what we need to do. It says, the weekend cost of producing X units in a manufacturing plant is given by the function d of x equals 40x plus 300. Now, if the number of unit products in t hours is given by r of t equals 80t, find d of r of t. In other words, it wants us to find the composition of these two functions. Now remember, I can write the composition like this, or I can write the composition like this. Either forms of the notation is the same. So I'm going to take my r function right here and I'm going to plug it in for x into my d function. Alright, so here's where we show this. Now I'm just going to simplify this by multiplying the 40 and the 80 together, and that'll give me 3200t plus 300. Okay, so there's my resulting formula. Now, from here, what does this mean? What do I need to do from here? Well, the model created by finding the composition of the two functions will be 3200t plus 300. Now, on your test, I may ask you to go a little bit further. I may ask you to evaluate it for a t-value. So be prepared to do that. This is going to wrap up the test 3 review for today. When you come to class next class period, we're going to work through this problem set together within our groups. And then when you go home, I'm going to send this review practice test home with you to further prepare. Okay, I will see you in class.